Hey guys, welcome back to a C devlog. Now, this is the first time I'm recording in Linux, and I can already tell that the audio is not going to be the same, so I apologize for that. I've tried to make it reasonable, but it just sounds kind of a little robotic, and I don't know if I can really fix it. So, at least for this one, I think it's just going to be this way. But I'm running Linux because this is where I'm actually programming, and I want to be able to actually show the compiler in action to discuss things that I've been working on. As per usual, this isn't scripted, and this might get a bit rambly at times, but last time that I did one of these videos, I talked about issues with null and nullable types. So I implemented a version of them that didn't work, that kind of worked, but didn't work well. And I'm not really going to show that because I would have to go back in my commits, I think, but I can kind of show what I've settled on now because I had a revelation yesterday and I found something that I think works pretty well. So the layout of this project, I think I've shown it in GitHub a little bit, but it's sort of just I have a bunch of files. I have to build it using Gradle, and then it takes certain arguments, like, again, like I said, a little bit rambly, but basically you pass it like files and some arguments and stuff. Really, it's going to be using like this bash script. And I've sort of had this script and been working on it and polishing it for a while since I've been working with C every time I redo a script like this. And basically the idea is you can specify directories, not just individual files, and it will find all of the C files in the directory and it will pass it to the compiler, so it will compile all of them together and it will just output them all. Is this supposed to be like this? I have no idea, but that's okay. Maybe. I probably copied this command from somewhere else because I have no idea what it does. Other than it... Yeah, okay, so anyway. In order to sort of make this easier, because you see, it's going to... When I call c.bash, it's going to do a bunch of stuff, and then it's going to run the program with all of the arguments we pass, and then the output directory for it, and then all the files individually. So instead of calling c.bash each time, because then I'd have to do gradle w dot and make it build and stuff, I have a simple makefile, which simply, when it builds, it uses gradle to build, and then it unzips the resulting zip file, so I have access to like the actual jar that I can then run. And I believe that's what's going to be called by cbash, because the whole point of this is that you could have just the app by itself without the source code, of course. So you could just build it and then deploy it, or I mean, like, distribute it that way. So my makefile it will build it, and then it will get rid of the output directory, which I have a little test folder here where I can make C files and it will output stuff. Okay. So yeah, all I'm passing is the entire test source directory into it, outputting into test/bin, and I'm enabling debug, so it will produce a debug thing so I can see what it's doing. Okay, so the first thing is I have this standard file, which when the compiler runs, it will produce this file in the output. Wow, I'm jumbling words. It will produce this header file in the output, and then all the other files that you end up producing will include this file. And all the header this is just the standard stuff for C. It's a handful of headers, so like limits, standard define, standard defs, standard ints, so that I have access to this stuff. So you can actually see how I'm defining all of my types. Now, anytime I produce a variable or anything in C, I always have its name look something like this. So for example, C type or C var or C fun, so that just so I don't have any namespace collisions. So now you can actually see how I'm exactly defining these types. For a nat16 is defined to be a uint least 16t, which I believe is the compiler will create a macro, create all these macros in the, I think it's in standard int, and it will It will figure out what this is for your system. So uint, meaning unsigned int, at least 16, which I think means it's at least 16 bytes, but it might be more. Or it's the smallest one that can hold 16. I don't remember exactly how it's defined, but essentially that's how these types are all defined. So for example, an int 64 is not guaranteed to be 64 bits. It's just, I think it's guaranteed to hold 64 bits in terms of like the size of that the number can hold or whatever. Bool, I'm using standard bool. Bytes, my byte type is essentially an unsigned char, which I'm defining specifically as this, and I'm explicitly using char for this, so that if you use like functions from C itself, and you're passing like a char pointer as a string, that way all the types will work out and stuff. You see a nat is just an unsigned int, int is just an int. Now for the naming of like my reals and imaginaries, it's essentially the same thing, but it's kind of misleading. So like a real 32 is a float, which is reasonable because a float should be 32. And then a real is a double. And then real 64, that's a long double, which actually won't be 64 bits. It's going to be like 80 bits or like 120 depending on your system. But I just figure it's at least can hold a thing that size or whatever. Like it's just a common naming thing because I didn't want to include the concept of long and short because that's just messy. And then the complex types. So what I've done for nullables, originally, if data was nullable, it would just be like, you'd have an int x is 5. And if your data is nullable, it would be like, you have a pointer, well, this would be called like xval, and it would make a pointer x. And then it would be like, is this thing that you're assigning to null? It's essentially like, you'd have to do, this value is something, and then you set x to that, essentially. It's not going to work exactly because of a handful of reasons. Mostly because we're making global variables here, so it's going to complain about it being not compile time constant stuff. But just for the example, it would be something like this. You would set the pointer. You'd have to use the comma expression so that you could set the value of the value here, and then actually have a pointer value here. And then when you're using nullables in expressions, you would always be dealing with a pointer and a memory address. So you'd always have to check, is this pointer null? And if it is, then you have to do stuff, and it was just messy. So my solution to that, if I clear this out and save, is using structs. Now, originally, I considered doing this, but I thought it wouldn't be... I didn't want to do it because I thought it would take up more memory. But what I realized is... So the structs are all simple. It's just there's a boolean to keep track, is this thing null? And there's a value to keep track of the value when it isn't null. So actually, what I discovered is, at least given the compilers I've used, this will depend on your compilers because different compilers will pad structs differently so that they like line up with like at integer sort of sizes. So like 1, 2, 4, 8, 16, like powers of 2 sort of memory address sizes and whatever. So even though, for example, I'm using, what's this called? It's a bit, I don't know why my mind is blanking, but essentially I'm saying this, if possible, this should only take up a single bit because it's a boolean, so it doesn't need to take up more than 1 bit. But the compiler will still, so for example, a byte is a single byte in size. And a bool could just be a single bit, but in practice it's going to be a whole byte. So this whole thing is actually going to be 2 bytes. But that's not actually a big deal, because otherwise I would have needed a byte, which is a single byte, and a pointer to a byte. And a pointer to a byte is 8 bytes. So it would have been 9 bytes, but doing it this way is only 2. And not only that, but this notation to specify that this should be 1 bit actually works with the boolean. So whereas without this colon once bit syntax, this would be 2 booleans together. So this would take up 2 bytes. But actually with this syntax, they can share a single byte. So this Nullable Boolean type only takes 1 byte per thing, whereas before it would have been a byte for the Boolean and then 8 bytes for the pointer. So instead of 9 bytes, it's only a single byte. And this sort of works for all of the types. All of the types that aren't 64, the value is going to be less than it. The only issue, the only time it isn't saving memory, are for the floating point long types, essentially. So like these, the long double, quote-unquote 64-bit types. I believe it would, with the pointer and with the raw value, it would take up like 24 bytes, but that has to be padded up to like, I think it would have been 26 actually, by default or something. It depends on which one it is, but it has to pad it up by like 8 bytes each time. But that's the thing, right? The more commonly used data, I'm saving memory, and the less commonly used data will be a tiny bit more. So overall, I think it's a good improvement. But what really matters is how simple everything becomes when, oh my goodness, when you use it that way. So for example, I can declare a variable x and set it equal to 5, and this is not nullable, and you can notice that there's type inferencing and stuff. It figures out that this is an int, and then it actually sets the value in C. And I have a nice comment just to show the type. So I could use casts and stuff because I have implemented that, but I can also just define, well, actually, this should be a nat, for example. And it will just set it this way. If you do something like, note that this works because this, so like internally, this is still an int, but because you can assign an int to a nat, cannot assign int to type nat. So actually you couldn't implicitly do this. You would have to cast it to make it actually work, because you see the language complains. And you would just do a cast. And at compile time, that essentially doesn't even matter. It just kind of goes away. In fact, it's like equivalent to doing this, which is another sort of syntax from C that I don't want to implement because I don't like how it looks and how it tends to work. But it's essentially equivalent if you wanted to do it. Now, I should probably actually implement nullable types, or show nullable types. And again, I should probably use an int for this, or a higher level thing that you can cast to. So, you see it will compile it. It declares it as a nullable int, which is a struct. And so, it has to construct an actual struct using an initializer list where it's not null and the value is 5. And now, this is incredibly useful, because before I had to deal with having pointers and expressions and stuff, but now everything's just a normal expression. And the good thing about initializer list syntax is I could come here and like take the value of this expression. And so I can actually use this in terms of other things. So if I, for example, if I make var y and I just set it equal to x, it will infer the type and it just copies it. Because copying is already a thing for structs in C, whereas before, when I was copying nullables, I had to not directly copy the pointer. I had to check, is this thing null? And if it is null, just set it to null. Otherwise, copy the value using dereferencing. But that was just so messy and such a hassle. But here, C implements copying of structs. And for example, I can even change this to a real. And you see it figures it out. Now, actually, this is kind of okay. So essentially what it does is it creates a new struct, this type, a nullable real. It just takes x's is null component, and then what it does is it takes its value and it casts it to a real, which is exactly all it has to do. So like that works. Now there are some issues, not really issues, inefficiencies where suppose I cast this to a nat nullable type first, and then I assign it. Well, then it's going to start to get messy because it's actually going to do the cast twice. First, it's going to make this thing, which is the actual cast value of x to nat, and it's a nullable nat where It takes the null and it casts the value. And that checks is that thing null, and then it does it again, but it takes the value. Now, that's not ideal, but I'm okay with it for a handful of reasons. One, it's your fault if you type code like this. Unnecessary casting, that's up to you as a programmer, you know, like you just shouldn't. You can optimize it away by just not doing that. And two, even I checked with GCC with level 1 optimizations, the most basic optimizations, it produces exactly the same code whether I do this or if I like intentionally sort of like make it simpler. So it should optimize away, so I'm not concerned about it. Not to mention, you don't have to do this type of stupid casting thing. And there's ways to get around it as well. You could, for instance, create it like an xval, which is of type int, and you could set it to, for now I just have to assert that x isn't null, which would essentially take the value. Actually, what you can do is you can set it directly to a nat, and that's not how casting works in my own language. And then you can cast the value, and then you could do this. So suppose the casting actually did something important. I think this should work. It'd be kind of funny if it doesn't, but let's see. So you take the value, which asserting that it isn't null just takes the value. So of course, in Kotlin, when you assert that something is not null, it will throw a null pointer exception if it is. But C, not having exceptions, I'm not going to mess with that. I'm just going to let errors happen if they happen. If you falsely assert that something is not null, and it is, that's your fault, and whatever happens is unspecified behavior. So I will add other operators. The operators I was talking about adding before, the null safety operators, I think I actually know how to add now that I have this framework for nullable types. So you see, if you wanted to do that stupid cast because it changes the value or something, all you have to do is assign the value somewhere, assuming it isn't null, or you could do certain checks or whatever, cast it and then insert it, and it's a lot simpler. Like, you have ways around it as a programmer if you see what it's producing, but otherwise it will just directly do this. And also you can, whoops, you can also cast nullables to not nullable. And essentially that does the exact same thing as the not null assertion. Is this actually doing what I expect? It's taking the value, it's casting it. Maybe I need to change what this is doing, because this is actually keeping it. Yeah, okay, so that's a bug I found. Okay. But in principle, if you casted a nullable to not nullable, it would be exactly equivalent as this. It would be exactly the same as saying it's not null and then casting it. I think that's good. Like, it might happen that you do it by accident sometimes, but I think if it's nullable, you should just keep that there. Maybe I could add a warning or something, but I think it's fine, I think. Because it's going to, I don't know, maybe I should have a warning or something. But also, what if I make an int on the heap, which I've also sort of implemented, and it's a nullable int on the heap, and I set it to x. Well, we have our same x from before, and then when you declare y, it would have been a lot harder before keeping nullables with pointers, because like I said before, it would have been you have some value is equal to something, and you have a pointer to that value. And if the pointer is null, then the whole thing is null. Otherwise, you take the value, which is a big pain. But it's really hard when you're dealing with malloc and the heap, because you don't have this value component, you just have the pointer to some memory. So I would have to be freeing a lot of memory a lot of the time and then mallocing again. But now that I'm doing things this way, once you declare a variable on the heap, it will just malloc it once. And theoretically, if this weren't a global variable, at the end it would call free the last time it's used automatically. But I haven't done that yet. So you malloc a size of a nullable int, which, because C supports mallocing structs exactly the same as everything else. And you see, yeah, this is complaining again because this is in the global scope, but it's supposed to be inside of like a main. So I think if I just make a main, you see that those go away because this is sort of where it's supposed to be, but I haven't implemented functions yet. So what it will do, it simply mallocs the memory and it just sets the value. It'll just copy it, which is fantastic. And I think there's a lot of other stuff I've implemented. I don't want to show necessarily everything, but this just makes it. And then I already have an X. If I have a Z of type nullable int and I set it to Y, anytime you reference a dynamic, which is, you know, a heap variable, it will, anytime you access it, it just auto does this. This is just what happens. It will auto, every value is going to be an actual value, not a memory address. And now that I have, you know, these, it actually is going to make sense. Now there's one big thing, of course. What happens if malloc returns a null pointer? Well, this dereference is going to fail. But that's what I'll have to do in the future is I either have to make something that allows the programmer to check if this thing is null, because notice, I don't have pointers in my language, not directly. So I could do something like, I don't want to do like a property, but like Python has like a length function. I could do like something, it's not going to look like this, but something like this, good alloc, which is like a global function, and you can just pass in like a heap thing, and then this will return true or false, of course, and then you can check yourself, be like, if this thing is true, then do stuff. Or I could make the programmer check every time, which will be a lot easier in the language and a lot more efficient. Or what I can do is I can make an allocation function that when malloc returns null, I either exit the program or I jump to a function that you could create to handle it in some way. That'll be a bit less efficient because then I'm always checking. And there are times like malloc will essentially never fail on like a desktop computer in a lot of situations. Like checking malloc to if it's not null is mostly going to be for like an embedded system or a system that is using intentionally as much memory as possible. And you don't necessarily just want to auto fail a program, because some programs may be able to pause and then like free memory from certain threads or something and then retry the malloc, which is why it's good to allow the people to handle it themselves instead of forcing the language to just crash after. Because you're not only going to be making like desktop applications with this, and even if you are, you should probably check if malloc actually succeeds or not. So in the future, I'll have to find a way to actually check that. But for now, you kind of see the proof of concept here, where because of this breakthrough of making these structs, everything just becomes kind of like really simple when it's figured out. And so I'll actually be able to implement these operators, I think. The access one's going to be weird, but that's just because accessing in general is going to be weird since I haven't implemented structs or anything, and it's going to be kind of challenging to... I'll have to, like, because the way the type system works is it has to know the type of everything. So when you access, it has to know what your struct is and what all the types of all the properties are and what the properties of your properties are and stuff. And so it's going to be interesting, but it should be doable in the future. This is my next step to actually implement this null coalescing operator, and I think it's kind of okay. I don't think it's going to be that hard to do, because all I really have to check is like, I think at runtime I just have to check like y.isNull, and if it is, return y, otherwise return z. The only thing I really have to be careful of is if these things are null, if either of them is null. Because the way I'm handling null, let's see, if I just do this, you see that there's nothing there, which I also should really change, I think. I don't know. Basically, I could, if I set a variable to null, that's probably a better demonstration. Notice, of course, that if you just say this It will complain that it can't infer the type, of course, because there is no type. It's of type any, but it nullable any, which of course doesn't exist over there. I still produce output, but whatever output is there will not work if this thing produces errors or failures. Warnings it should be fine for, but so I can make, let's be a bit more interesting, make a nullable real. And so what you see is before, if we just say null, null as an expression is nothing except a type. And it's a type because, for example, you could cast null, you could do it this way. You don't have to use the type syntax, you could just cast null to it and then it can infer it. And it does the exact same thing. If you prefer to do that, because you're just casting it. So what it does is it figures out, it keeps track, it knows it's null because there is no value there, it's a constant expression. In fact, null is the only constant nullable expression because I don't allow values to be constant, and I suppose I should demonstrate what a value looks like. If I say this is 15, you see what I actually do over here in the C code is I just use a hash define to make a value, which will be a compile time constant, which is why this has to be constant. And I choose to not allow them to be null because to me it doesn't make sense for a value to be nullable, because the whole point is that it's an option at runtime, but a value isn't supposed to be a runtime value, it's a compile time value. You should know what it is. So you see the first one, it can't infer type, but then it also cannot declare a nullable value. I don't even kind of remember why I started talking about values, but yeah, there's values for hash defines, there's variables for data that can change, so I can reassign X, and there's invariables for things that can be assigned once, but cannot be reassigned. That's sort of like a const in C. And yeah, so you can declare null. But it essentially is nothing. It just figures out, okay, we just have to make this initializer list. I don't remember exactly how I got into that discussion about null. I mean, this whole video has kind of been about null. Oh, yeah. So the null coalescing operator. If you have null on these sides, you have to be careful because this thing itself doesn't have any sort of value. It's just a type or whatever, but this will throw a warning, of course, but it's not going to fail. And in terms of types, well, that's the thing, right? It's okay. I just have to deduce the type. This, for example, will simply become null. This will just become equivalent to null, and it will throw a warning saying that left-hand side, anytime the left-hand side's anything, it will just always return the right-hand side, which in this case will be null, which will have no value, and it will be treated exactly like null. But suppose this is 50, if this is some unnullable value like X, then if you say, it's interesting. So when I have this syntax alone, I kind of prefer it that way, but I think what it's supposed to be is if you have like a.b, if you have a.b.c, it's sort of supposed to be like that, where it's like, you do like your checks and then it's like, is all this thing null? If it isn't, then you do this. I don't know. Because I used to, with the ternary, again, this is like off topic. I used to always do my ternaries like this, where it's like true, 1, false, 0, or whatever. But I've recently really liked to do this because it just looks more readable to me. It's like true, question mark, then this, otherwise this. So I prefer to sort of keep it there. But with this, I'm not really sure. I don't really like how that looks, but it kind of, I guess I could also do that. But that's, no, I guess I technically can't because it's one operator, but yeah, I don't know. Anyway, the previous one would just return null. Now, when it comes to this, where X is nullable, what I have to do, let me think about this. What I'll have to do is I'll just have to check. In C, I'll have to say, like, X is null. And if it is, set it to X, otherwise null. And the important thing is the type. So, since one of them is null, the type of this thing is just going to be the type of the thing on the left. And if the thing on the left is not nullable, then I can throw a warning, and then I can just return the left thing. But in this situation, I would have to do that. And then I also, the other thing I have to do is I have to infer types here. So I think what I'll do is essentially exactly the same as if I did like x plus y, except of course the imaginary stuff I'll have to figure out. So like if you have a real on one side and an imaginary on the other, I guess the whole expression just becomes complex, because that's just how it has to be to allow you to assign both. And when I add more complex types like arrays and stuff, it's going to be more complicated, but I'll figure that out. Essentially, they just have to be able to be brought to a common value so that the whole expression has a type. But yeah, you'll also notice I have to reference things twice, which is sort of the reason that previously the optimization was, the casting example was really weird. The other option I have is I could store it as a temporary, but of course, so could somebody else. So I'd rather not force it to always store temporary. Now, what I do have to be careful of is function calls. Because if you do a function call in that expression, it would call the function twice, which is not only inefficient, but might modify a state somewhere, which is dangerous, or it might return something different each time, which is even worse. So anytime I call a function, essentially, I'll just have to store the value temporarily. And then what I get to hope is that the C compiler is smart enough to optimize that away if it's not needed, which I think it really is. I'm pretty sure the C compiler is smart enough for that. So I do always have to remember that. There's optimizations I can make, but at the end of the day, the C compiler is what's going to truly optimize code from this. But yeah, I think that's like a pretty good sort of showing of what I've been working on so far. And I've sort of solved the issues that I've been having. I also implement, I guess while I'm here in this video, I may as well also showcase ownership that I've implemented. Var y is equal to ownership of x. So it's essentially just how you make a pointer. But now if you try and reference, if you do like x plus 2, you'll see you're not allowed, because only one thing is allowed to talk about this at once. And you're giving it to y. So x becomes a dead identifier that you can't reference from anymore. But y will of course hold the value of x, because if I just like print y, it should also dereference automatically, just like nullable, or just like dynamics. Now if I set this to be, say, a dynamic integer, and I try and assign it to this, where this is a stack integer, hypothetically I could make it work, right? I could, but I'm making it so that it has to be the same type entirely. You can't, this should do nothing except make a pointer to the thing, and the pointer types have to be the same. So if you want to switch from the heap to the stack, what you have to do is you have to simply make a temporary, essentially. And you could make this an int and set this equal to x. And then you could set this equal to ownership of temp. And now that won't do exactly the same thing as this, because now x is still available. But fundamentally, ownership is just a way of dealing with pointers. It's not really about like who controls x. It's more just about, I want to pass this value somewhere, so I'm going to pass it this way. And let me actually make sure that worked. So I set 5 equal to this heap value. I dereference it, store it temporarily, and then I set this equal to the pointer to that. Yep. Okay, and if you want to make static variables, for example, you could, in principle, do that. It's not going to output because I'm making something I didn't really realize, but makes a ton of sense, is that C global variables, these variables are static. They exist on the data segment of memory, which is why they need to have a static initializer as in a compile time constant. These always will be on the data segment of memory, which is why they are, well, it's what makes them global. It's because they can be accessed anywhere in the program because they're in the data segment, not on the stack or in the heap. So in the future, once I implement functions, I'm going to require all global variables to be explicitly labeled as static. Simply because I think it makes the most sense to the programmer what's actually happening here. So you'll actually just have to say it's static. And you can make a static to anything, For example, if you made a static variable that is on the heap, what is actually going to be static is the pointer. The issue is at some point somebody could come along and free that memory. But I guess that's not really true because that's the thing, right? Like, that's the whole point of ownership. If I have a static variable A of type int on the heap, and I set it equal to 10, you notice that the static goes away because it always goes away if it's global. So you malloc it, and you have the pointer here, which is now a global variable, and then you'll set the value. I suppose actually I can't. Now that I think about it, I mean, look at it, right? You can't have globals that are this. That just doesn't work. So what happens if I int main, some live sort of debugging here. If I do this, and I explicitly label this as static, so I simply cannot have, I actually can't allow static heap variables because the result of malloc is not a compile time constant in EU. So this actually could never work. I guess I need to add a error then so that you can't have static heap things, which sort of makes sense. It kind of makes sense. Well, actually you can though. You can. It's just, it would have to look like this. You cannot initialize a static heap variable in the declaration, but what you can do is this. So you can declare it once, so you can have it in your global or whatever. You just cannot initialize it until later, which is fine. And then if you took ownership of this and put it somewhere else into a non-static variable, I guess that's okay. And okay, so the one thing is I just have to prevent having any value initially if you're making a static heap thing, which I guess that's okay. Yeah, but so those are the sort of considerations I have to think about when designing this language. So if you wanted a language that was anything similar to this for some reason, those are the types of things I have to care about. But overall, I think I'm making pretty good progress with this, and I found a way to actually sort of do this. For functions, once I implement functions, these sorts of parameters aren't going to be too big of a deal because it's just a single struct instead of a pointer and a value, which actually, like, I didn't even think about that, but that pointer value, like having two variables to represent one sort of thing, would have been a nightmare when it came to functions because you would have had to pass in both in case the pointer was null. It wouldn't have been pointing to the data, so if you tried to reassign it in the thing, it wouldn't have worked, and it would have been really annoying. But now it's like the gates have opened up, and I've just found the way forward, and it just makes sense. And not only does it make the code so much simpler, let me actually showcase it again. Not only does it make the code like so much simpler than it would have been before, it also saves memory most of the time because of like the sizes, as I mentioned, the size of a pointer always being like a 64-bit integer. So yeah, I think that's going to be it for this episode. If you kind of like this style, or if you like me actually showcasing the code and how it works, let me know. Hopefully the audio is not too bad. But yeah, thanks guys. I'll see you guys in the next devlog.